Welcome back, everyone. In this video, we're going to get an introduction into climate science. And so after reading the section of the ebook and watching this lecture, you should be able to describe how incoming sunlight and outgoing thermal radiation from the Earth are used to regulate the temperature of the Earth. You should be able to explain the underlying mechanism of the greenhouse effect, describe characteristics of greenhouse gases, and then interpret graphical representations of some simple climate data. So let's begin with this interlude on climate science. The way you can find this is by going to section lesson 1-7 of the ebook. Click on the stop sign. And there it talks about the climate change and the greenhouse effect. So the purpose of Chem 110 in general is to help you understand the basics of chemistry so that way you can use that information to make informed decisions about the world around you. And a couple times during this semester, we're going to talk about the phenomena of global warming and climate change, how the greenhouse effect and pollution play into that. And so this is going to be our first introduction into that. So something I'd like you to think about is, what is your opinion about global warming? Which of these three statements best describes what your stance is on this? Pause video and take a moment to think about this. Okay, welcome back. So let's now talk about the science of global warming. To understand what's happening in terms of climate change, we first need to understand and revisit black body radiation. We discussed this briefly in an earlier video, essentially talking about how black body radiation and understanding it helped us to understand that light behaves as a particle. So, what is black body radiation? Well, you see it actually very frequently if you ever go to your kitchen, turn on the stovetop. If you have a heated coil stovetop and it's cold, then it'll be kind of this darkish gray black color. But as you heat it up, it becomes more of a red color, and then orange, and then yellow, and then a very, very bright yellow, almost like a whitish color. And the reason for that is because it is behaving similarly to a black body. And a black body is an object that can absorb and emit all wavelengths of light. And some of the properties of it is that the emission depends upon the temperature of that object. And in fact, all objects emit radiation, even you. I went and did the calculation. You can determine the maximum wavelength, the wavelength that corresponds to the highest number of, or the most abundant wavelength that's emitted. And for the human body, when you do the calculation, it turns out that we emit wavelength, the most abundant wavelength is 9.4 micrometers. This is in the infrared spectrum. That's why you cannot see the emission that's coming off of you, but you can feel. That's why your body emits warmth. Okay. Another property of black body radiation is that the intensity of the light increases with the temperature. So not only does the frequency or the wavelength of light change with temperature, but the intensity also increases with temperature. Let's take a look at that. So looking at these two aspects of black body radiation, you can go to the ebook and click on the Diving Deeper icon in Chapter 1, Lesson 7, and you can pull up a simulator. And this application there, it allows you to vary the temperature of a black body object and see what wavelengths of light are emitted. So the first thing to recognize here is that we have a range of wavelengths emitted. And that's what we said. We said a black body, a perfect black body, is going to emit all wavelengths of light. So we have a range, and it's emitting at different intensity. We also, this is a low temperature. So when I plotted this was low temperature black body. And I'm going to have to erase this because I'm going to pull up another one. If you have a higher temperature, what we notice is a couple things. Notice that the scale of the intensity changes, so our overall intensity changes, but then also what we are calling the lambda max, the peak, the most abundant wavelength that is emitted, is also shifting. And we're shifting from high wavelength to low wavelength, or in other words, low energy to higher energy. Because remember that energy, while it is directly proportional to frequency, is indirectly proportional to wavelength. So again, changing to the highest temperature, we see that indeed the wavelength of maximum emission continues to go down, the intensity continues to go up. And so these are common properties of blackbody radiation, is that the wavelength that's emitted depends upon the temperature, and the intensity also depends. It increases with the temperature. Now, how does this relate to global warming? Well, to understand that, we first want to talk about the greenhouse effect. Let's take our planet Earth. If we have the sun and it's emitting light, shining light on the Earth, then the sun's emitting that light, the Earth is absorbing it. And what happens is the clouds and the gas particles in our atmosphere trap in the energy that is given off by the sun and absorbed by the Earth. So glass itself is transparent to sunlight, but it absorbs thermal radiation, which is in the infrared. So greenhouses made of glass have this effect. Greenhouse gases are elements that behave in similar ways. So three common greenhouse gases are water, carbon dioxide, and methane. And these are gases in our atmosphere that absorb infrared radiation and allow visible light to go through. And so these gases are essentially the glass that covers the Earth. And it allows it to keep the Earth about 35 degrees centigrade warmer than it would be in their absence. So what we know is that the sun behaves like a black body. It emits all ranges of wavelengths of light. Some of that light hits the Earth and is absorbed, and then it gets trapped in the atmosphere of the Earth, keeping the Earth warmer than it would otherwise be. And so what we see is that the temperature of the Earth actually results from a balance between the energy that's absorbed and the radiation that's emitted from the Earth. So this plot you see in the ebook, it's a little bit complicated in the sense that we see that here the energy that is given off by the sun is scaled by a factor of 1,000,000. So really this should be 1,000,000 times larger compared to the scale given for the Earth. We shrunk it down so that way we could see them a little bit easier. What's most important to see here is that the emitted light from the sun, which comes in at a temperature of about 5,800 Kelvin, is absorbed by the Earth, and then some of that light, the infrared light, is radiated back by the Earth. And the temperature of the Earth is going to be stable when the total energy absorbed is equal to the total energy emitted back by the Earth. So we have this cycle. Energy comes from the sun and then is re-emitted back by the Earth. And so long as the total energy given off by the Earth is equal to the energy absorbed by the Earth, then our temperature is going to remain constant. And that's thanks to the greenhouse effect. Without our atmosphere, as I mentioned earlier, then we would be about 35 degrees colder on average than we currently are. And that would have devastating effects for the Earth. Right now, it is winter in the northern hemisphere. If it is, let's say, 10 degrees centigrade outside, we would actually be 25 degrees below zero. Everything would be frozen over. And the temperature swings between winter and summer would not get us to a very high temperature, relatively speaking. Our summers would be very, very cold. So the greenhouse effect is actually a very good thing. And it's what allows us to have life, essentially as we know it here on the Earth. Now, in terms of the energy that's radiated from the Earth, there's a couple things to notice. First of all, a large fraction of the energy that's radiated from the Earth does not escape the atmosphere. So if we take a look at our Earth, let's call this the atmosphere, some energy goes through the atmosphere, but most of the energy gets trapped and bounces back. And so it's trapped. Think of it like being surrounded by a nice warm blanket. And so that's what allows us to have our livable temperature, is that it's trapped by the atmosphere, radiated back to the Earth. So if we look a little bit deeper in terms of the energy that is absorbed in from, or that comes in from the sun, we can see that in some cases that energy is reflected back, whether it's by the surface of the Earth, by the clouds, or the atmosphere itself. It's reflected back towards the sun. We also have some light that is absorbed by the atmosphere. That's about 19%. And we consider that by the clouds themselves or by the gases within the atmosphere. About half of the energy that makes it to the Earth is actually absorbed by the surface. And then what we see is that in some cases, we have that energy that's carried back up to the clouds, which might make it back down and is trapped in that cycle. In some cases, it goes and is radiated out into the atmosphere as well. And so what we see here is that there are a variety of different methods and means by which the light energy is trapped and recycled through to the Earth. It turns out that the light that arrives at the edge of our atmosphere is different in terms of its total composition compared to the light arriving at the surface of the Earth. So before it reaches the atmosphere, we would have the yellow portion of this diagram. And what we see is that after it gets through the atmosphere, that some of it is filtered through. And so the energy that reaches the Earth itself is mostly in the visible and infrared region, whereas it was higher UV before it got filtered through. So the atmosphere itself is filtering out most of the UV light. About 70% of the UV light gets filtered through. And it does filter through some of the visible and infrared, but the vast majority of visible and infrared does make it through to our Earth. And then the energy from the Earth is radiated back out into the atmosphere. Let's take a closer look at that process. So again, the Earth is radiating heat or infrared radiation. The atmosphere, which behaves like glass, as we described, is transparent to ultraviolet and visible light, but it traps in and absorbs infrared light. And so this is what brings about, again, the greenhouse effect. About 84% of the energy is absorbed by gases in our troposphere, which is mainly due to the water and due to carbon dioxide. This is part of why carbon dioxide is such a big deal, and monitoring the carbon dioxide levels has been done over the past few decades to be able to model what effect that will have upon the temperature of the Earth. So what we see is at the surface of the Earth, what is initially escaping is higher than what actually makes it out. What we see here is that some of the infrared radiation escapes into space. That's what is indicated here in this kind of salmon-y color. And the green indicates the light that that essentially bounces back, is re-radiated back to the Earth. And so to understand why this is happening and how this is happening, we need to look at how light interacts with matter. In the previous video, we talked about how depending on what type of light is interacting with the matter, it's going to cause different effects. So with infrared radiation, which is the light being emitted by the surface of the Earth, what that does is it causes the molecules to stretch and to bend. It causes vibrations within carbon dioxide and water and ozone. And those vibrations trap in the energy and re-emit it back down towards the Earth. And that keeps the heat from being released back into space. And as I've mentioned before, this is a good thing. Without the greenhouse effect, we would be about 35 degrees colder on average. Most of the water on the Earth would be frozen over. And so this is really a good thing. So how does this tie in then to climate change and to global warming? Well, carbon dioxide levels have been rising, and the concentration has been a very good predictor of global temperature on average. So this graph, which you can find in the ebook, is indicating the cycle of carbon dioxide levels to temperature levels over the past 800,000 years or so. It's the concentration of carbon dioxide is measured in parts per million. And this is essentially saying the number of particles of carbon dioxide per 1 million particles of atmospheric gases. So the highest previous concentration, which is about 330,000 years ago, was 300 particles of carbon dioxide per 1 million total particles in the air. Okay? And what we see is that that temperature was about 3 degrees higher on average than where we are, where we have been over the past 50 to 100 years or so. Now, if we take a look at the average carbon dioxide levels about a year and a half ago, that is at about 415 parts per million. So it has skyrocketed relative to even the highest concentration in previous years. Now, we haven't seen this drastic temperature shift yet because we're still waiting for the total effects of the accumulated carbon dioxide to affect the environment. But we have seen over the past 100 years these shifts. Notice that the scale here is on hundreds of thousands of years. Okay, and so it's going to be, so we can see these trends over time. If we zoom in on the past 20,000 years or so, then what we see is that over the last 10,000 years, that there is approximately fairly level amounts of both carbon dioxide and then the temperature change. And we can see here, zooming in the last, within the last 100 years or so, 150 years, that there's been a dramatic increase of carbon dioxide levels and that the temperature changes are slowly trailing behind it. If that trend continues, then that could be a very devastating effect. If it continues in the same as before, we would predict eventually shifts of up to 10, 12, 15 degrees centigrade higher than what we are currently. And that would devastate the whole planet and the ecosystems that currently exist. The levels indicated here, we can see this is where we were at about 120 years ago versus where we are today in terms of the CO2 levels. The rapid increase of carbon dioxide coincides really well with the increased use of fossil fuels during the starting with the Industrial Revolution in the mid-1800s. And since then, the global temperatures have increased by about 1.5 degrees centigrade. Now, later in the semester, we're going to talk about the ethics of this and what should be done We're not going to focus on that in Chem 110 because we want to focus on the science of what's going on. However, I would encourage you to do some reading on your own and think about this and what would it mean if we were to increase the temperature, the global temperature on average by 3, 4, 5 degrees centigrade more than we are now. What effects would that have on the living conditions of people that are near coastal regions or areas that are already very hot and very dry? There are ethical implications for how we deal with this, both in terms of living conditions and in terms of economical conditions. And so it's a very important issue to be aware of and to think about. And so I would encourage you to think about this issue and what effects this could have for you and in the future. Thanks for watching and have a great day.